It's number 7. In this lecture series we're going to start talking about flow through soil. Okay, flow of a liquid, or sorry, a fluid, flow of a fluid through soil. Of course, in our case, geotechnical engineering, we are more concerned with, or most concerned with, the flow of water through soil. Okay, this word seepage is basically what it means is flow through soil. Okay, flow of a fluid through soil. Generally, we are concerned with the seepage of water. Okay, now we're going to start with seepage in one direction, okay, or one dimension, okay, and then we're going to move on to 2 dimensions. That is after we talk about stresses. Okay, so let's begin. What we have here is a slide that lists types of energy. Now, the reason why we talk about energy is because we know that flow occurs from one point to another point when there is a differential in energy between those 2 points, right? Flow always occurs from a point of high energy to a point of low energy, okay, and that is total energy. So when we think about flow, we have to think about energy, and so that we can properly go about analyzing flow. There are 3 types of energies: the kinetic energy, the strain energy, and the potential energy. Okay? The kinetic energy is associated to the velocity of the object. Okay, in this case is the fluid that flows. The strain energy is proportional to the, or associated with, the pressure. Okay, the state of pressure of the fluid in this case. And the potential energy is associated to the elevation of the fluid. Now, clearly, when we think of velocity, pressure, elevation, we're thinking about a point in the fluid. Okay, so when you think of energy, it's energy at a point. It is the velocity of a point in the fluid. It is the pressure at a point in the fluid. It is the elevation of a point in the fluid, the potential energy of a point in the fluid. Okay, I'm going to put here of a point. Alright, now we can analyze flow or calculate or solve problems associated with flow using energies, okay, but generally in geotechnical engineering and in civil engineering we use the concept of head. Okay, so what we do is we essentially say, look, let's convert all these energies that we know exist into the equivalent potential energy, and then that potential energy we convert it to a distance, into an elevation. So the word head is used to denote the equivalent potential energy at a point. Okay, that is, if a point has 3 units of kinetic energy and 2 units of strain energy and 0 units of potential energy, then we can convert those units into the equivalent potential energy, and then instead of using potential energy, we can use the head associated, or the elevation associated to that energy. Okay, so all this means is that we're going to talk about energy in units of distance, in units of head, okay, in units of distance. That is what it should be, distance in meters or centimeters. Okay, so when we say there's a point here, what is the energy at that point? We may say something like 5 meters. That's the energy. What we mean is 5 meters of head. Okay, and what we mean is that any energy that point is storing, let's say, any energy that point is storing can be described by these 5 meters of head. Okay, head. So we convert each form of energy into the equivalent potential energy and express it as the corresponding height or distance. Head has units of length, as you can see here, and this is something that throws students off. Students say, okay, the head is 5 what? 5 meters. Okay, if you don't say 5, if you do not have the units associated to the number, then everything is wrong. Okay, the units are very important. The third slide, which is shown here, it's basically a little bit more description of the energy. Okay, so we said, look, there's kinetic energy, strain energy, and potential energy. We said that in the previous slide. We can actually convert those energies to independent heads: kinetic energy, velocity head; strain energy, pressure head; potential energy, elevation head. Okay, and then we can use Bernoulli's equation. Remember that from hydraulics or fluids, right? So the total energy or total head is equal to the sum of all of them. So if you sum this head and this head and this head, you get the total head. Alright? This is going to be very important for us, the total one. Again, all of these have units of length. Alright. Let's move on to the fourth slide, and here what you have is a tank of water. So this is Fluid Mechanics 101, right? And what we're going to ask ourselves here is, what is the head, or what are the heads at these 2 points? Okay? Now, as you know, for all fluid mechanics problems, we need to have a reference line, or a datum, it's called. Okay? Here we're going to assume, or we're going to pick this as the datum, as the reference line. Datum. You could pick anything you want, right? You could pick any elevation. You could pick the top, you could pick half, you could pick here, whatever you want. But generally we try to, at least in geotech, we try to adopt a datum that is associated with some boundary of the problem. In this case, this would be a good one because it's the fixed boundary down here. Okay? Alright. What is the elevation head at point A? That's very simple. The elevation head is the distance from the point in question to the datum. Elevation head at point A. It is the meaning of elevation head is the distance above the datum. Okay? Or well, if the datum is up here, then it would be that distance, right? But generally we want to pick again the datum in a boundary, okay? Coincide with the boundary that hopefully is below the point, so that all heads are positive. Anyway, so the elevation head at this point is the distance from the datum to the point. So that is the elevation head. It's in meters. You can actually come here and measure, right? The distance. What about a point B? What is the elevation head? Very simple, the distance from the point to the datum. Elevation head at point B. Okay, so far so good. What is the pressure head at point A? Pressure head. The pressure head, as you remember from fluid mechanics, it is the, at this point in this case, let's say the head in the tank of water, it is the distance of water above the point. Okay? So, how much water is there above this point? Well, this much. Pressure head at A. Think of it as if you are scuba diving at this point. If you're scuba diving at this point, the pressure you feel is associated to this head. Okay? To this distance. If you're scuba diving down here, the pressure is higher, right? We haven't talked about pressure yet in this course, but it is associated to the pressure head, okay? Which in this case is this. Pressure head at B. It's that distance. Now, those are two heads, the elevation head, the pressure head. The other head that we are left over with is the velocity head. What is the velocity head at point A? Well, that is associated to the velocity of the point. Is that point moving in a tank of water? No, it's just a static tank. So the velocity head is 0 at point A, and the velocity head is 0 at point B. Okay? Now, what is the total head at point A? Total head is the sum of all heads at point A. Well, the total head at point A is 0, that's velocity head, plus that distance, that's the pressure head, plus this distance, that's the elevation head. This distance plus this distance is this distance. That is the total head. What about for point B? 0, which is the velocity head, plus elevation head, which is this, plus the pressure head, which is that. So the total head at point B is that. Look, the total head at point A is the same as the total head at point B. That distance is the same as this distance. And because the total head at this point, that is the total energy at this point, is equal to the total head at this point, that is the total energy at this point, then there is no flow from this point to this point, or from this point to this point, because the total heads are the same. Okay, that's why there is no flow in a tank of water, because the total head at each point, at all points, is the same. The elevation head is different. The pressure head is different, but that doesn't matter. What matters is the total head in terms of having flow or not. Okay, so make sure you have that in mind. Okay, let's look now at the case where we have flow. Now generally this slide is in PowerPoint, of course, and in the class I do not show the whole slide as you have it here. I go little by little, okay? So we're gonna have to spend some time in this slide explaining what everything is. Okay, so let's go step by step. First thing is we have a tube here, okay, like a pipe, okay, slanted this way, and we have flow going on, okay? Generally the students don't know that the arrow is pointing up, but you'll realize why it is pointing up in just a second. Okay, so there is flow inside this tube. Now, this is of course all based on fluid mechanics. We are basically reviewing fluid mechanics. There's no soil yet, okay? Now, we come in here and we place two sensors. This thin tube and this other thin tube. These are two different sensors that are going to capture flow characteristics at point 1. We do the same for point 2. We install two sensors, and the sensors are tubes, okay? All right. Now, this sensor here is called a piezometer. I'm going to write it up here. Piezometer. And it measures the pressure head. Okay? Why does it measure the pressure head? Why does it measure the pressure head? Well, you know that if you have a tube and there's flow, the velocity distribution is parabolic, right? The velocity of the fluid at boundaries is 0, right? So the level of water inside this piezometer is associated to what happens at the boundary, because the piezometer ends right here at the boundary, you see? So the level of water from this point all the way to here, that is the distance, okay, the water rises, is associated to the pressure head, because the fluid here in this boundary is under pressure, it's pressurized, but it is not moving because the velocity is 0. So the piezometer, this one, captures the pressure head and not the velocity head. Okay? Now, conversely, this other sensor is a thin tube that actually bends and points towards the point. So the pitot tube P-I-T-O-T space T-U-B-E. The pitot tube measures what? Well, look, it's actually in here like this, capturing what's happening in the middle of the pipe. At the middle of the pipe, the fluid is flowing with a velocity. The velocity is not 0. The velocity is some velocity. And the fluid is also under pressure. So the pitot tube measures the pressure head plus the velocity head. Okay? At this point. So if the piezometer measures the pressure head and it rises to this distance or this elevation, and the pitot tube measures the pressure head and the velocity head together and it rises for this point to this elevation, then what is the difference in elevation here? This is the velocity head at point 1, right? Look, pressure head plus velocity head. The difference must be the velocity head. Here we have the same thing. We have a pitot tube and we have a piezometer. That is the velocity head. That is the pressure head. Okay? So if we sum, well, before we get the total head, which is shown in red here, we should make sure that we complete everything by saying, look, the elevation head at this point is this. Now you may say, well, why? Well, I didn't mention, I assumed that you already kind of knew that I had assumed this, but so we should have said in the very beginning that this is the datum. Okay? Now you may say, hold on one second, how is it again that I select the datum, or I mean, how do I know which one is the datum? That is up to you. You can decide to have the datum anywhere, okay? But generally, we have some system below, or some boundary. In this case, let's say this is the floor or something, or just a line that is below these 2 points, etc., and below the system, and that's what we call the datum. Okay, so again, please don't be confused in thinking that you have to select the same datum that I selected. Okay, you can select any datum you want, as long as you make sure that everything is with reference, every distance you measure is with reference to that datum. Okay, in this case I selected this one, this line. Now in the exams I will tell you what to use as a datum, because if everybody selects a different datum, then everybody will have a different procedure, okay, in terms of calculation, but hopefully if everybody is correct, the answers will be the same. Okay, so remember, it doesn't matter what datum you select. If you select, let me just say it this way, if you select a datum that is up here, and I select a datum that is down here, and we do the problem, we're going to get the same answers, okay, for the case of total head. Okay, so for the case of pressure as well, but in general what I'll give you is, I'll tell you where the datum is or should be selected, so that then everybody has the same procedure and it's just easier to grade the test. Okay, so this is the datum that we select arbitrarily. This is the elevation head at point 1, this is the elevation head at point 2, right? And now we are able to calculate the total head at each point. It's just the sum, right? So here's point 1, elevation head plus pressure head. What's the pressure head? This. From here to here. So elevation head, pressure head, velocity head. And so H1 in red is the total head at point 1. Okay? H2 is the total head at point 2. So what do you have? Elevation head, pressure head, velocity head, H2. Okay, now going back to the datum business. If you had selected another datum, then I made a mistake. The total heads would be different. But what would be the same, which is what drives the flow, is the delta H. It's H1 minus H2. Okay? This is what stands regardless of what datum you choose. So I'll say that again. The value of delta H, which is what drives the flow, is going to stand regardless, it's going to be the same, provided that you do the problem correctly, and you determine this correctly, the heads. That delta H will be the same for any datum. The total head will be different. Okay, the calculation of total heads will be different if you have a different datum, but the delta H will be the same. Now, why is it that delta H drives the flow? Well, we know that flow occurs from one point to another point if there is a difference in energy, total energy, between those 2 points. So that difference is captured by the difference in total head, because total head at a point is proportional to total energy at that point. So the difference in total heads is like the difference in energy, or it is the difference in energy that drives the flow, and that is delta H. If delta H is 0, there's no flow between the 2 points associated with that calculation. In this case, the total head at 1 is larger than the total head at 2. Therefore, there is flow from 1 to 2. Okay? And the flow is driven by that difference. Okay. In the next slide, we have a definition that is very important in soil mechanics and geotechnical engineering. This is called the hydraulic gradient. Okay? And it uses that delta H that we talked about. Here we have written it in a form that is a kind of like a calculus form, okay, where you have an infinitesimal H and an infinitesimal length. Okay, so this delta H in an infinitesimal format is written like this, D. Remember the little d in calculus? That means small, right? Very, very tiny H, very, very tiny L. So what is I? That is a hydraulic gradient and is a ratio. So it's a rate. Okay? It is a rate at which the total head changes. Remember the little d is like a change in, right? Derivative. Well, not really derivative, infinitesimal, right? So rate at which the total head changes with length. Okay? So you'll see, for now I'd like you to just have this definition in the back of your mind. But you'll see later how it is written in a non-calculus type format, where we use actually delta H and L, okay? Because we have finite problems in engineering, so we don't have to use this particular equation. This is more like a generic mathematical way of writing it. But for now, keep it in your mind. It is a rate at which the total head changes along a length, okay? It is a rate of energy loss, okay? So for now, let's just keep it in your mind. This H, of course, is the total head.